Yeah, so I had some rather specific prepared remarks, but maybe, I mean, maybe can I ask some questions? Is that okay?
Where's the foundational questions institute? We are all about this.
Yeah, what is the question? Is reality discrete or...
Is it analog or digital or discrete or continuous? You can twist it to the way you pose it in whatever way you find most interesting.
Right, analog or digital. So, I mean, of course, one of the key things here is this word reality, which is a word that I think is highly overrated.
Plug your ears, Brandon.
Well, I think many things are over. Like consciousness is highly overrated as well. Like most people live their life in a very unconscious fashion. I mean, human beings have this way of I think it's kind of a protective cloak to try to make ourselves special. You know, that we believe ourselves to be conscious and other things are not conscious, like the table. And we have these kind of myths about ourselves and the world. And one of these myths is that there is a thing called reality. So now maybe there is something called reality, and maybe not. I don't know. So I try to think of these things. Most physicists, and I'm a physicist by training, despite the fact that I'm a professor of mechanical engineering, tend to think that there is a real world, and that we're making models of the world, typically mathematical models in the case of theoretical physics, that there is a world out there, and we're making models of it, and that our models correspond to the world, and we're getting better and better approximations of reality. And this actually has worked really, really well for physics for a long time. But in some sense, you know, I think physicists, I feel we should be a little careful and humble about this. I mean, if you look at what happened with philosophy and the notion of reality, so I actually I started doing the work I'm doing on quantum information and quantum computing by doing an MPhil in history and philosophy of science at Cambridge University. And I was just really stunned. I mean, it was a real shocking experience for someone whose background was in physics to study philosophy. You go to the weekly philosophy seminars, and some philosopher would get up and say, "The truth is blah 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 blah," and another person would bang on the table and say, "You're absolutely wrong. The truth is blah 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 blah." And I would go to myself, "Oh, blah 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 blah. Those are exactly the same thing." And what I realized after several months, I was getting very, very frustrated, is that philosophers were trying, and still try very hard, to use words to pin down what it means for things to be real. And the reason I did not go on in philosophy, because I felt that words were inadequate to pin down how things were real, and if I wanted to use kind of rational kinds of thought to pin down how things were real, I better go back to physics, which has a much better, I'd say, track record at having a contact between mathematical theories and reality. But that doesn't mean that this perspective is right. I mean, I think in the case of philosophers, it's actually in some sense incorrect. And if you look at a famous Cambridge philosopher, Wittgenstein, he was Austrian first, then he came to Cambridge, then he actually gave up on this whole notion of talking about reality in terms of words. In his first book, Tractatus Logico-Philosophicus, a book which, by the way, was his PhD thesis but had no footnotes, which I thought was really kind of great. If I had the balls to write my PhD thesis without footnotes. Like, he has this thing in the beginning that says, there are no footnotes in this book. That's not because people haven't written things that are relevant about this, because of course they have. And it's not because I don't know about them, but of course I do. But because this book is self-contained in and of itself, and no footnotes are actually required. So, he got away with it. Okay, but in that book he tried to pin down the nature of reality in a very specific fashion, which in fact is what we would recognize now as appealing to the theory of computation. He was appealing to the after all the little, if you've read the book, it's got like, after all section 1.045 and section 1.046 and everything like that, the core of the book is Wittgenstein's having read and realized that you could construct any kind of what we would call a recursive function out of simple logical operations. And he thought that should be the basis for describing reality, which I suspect we're going to talk about a lot today, because a lot of that you could say that if you unpack it, what the Tractatus Logico Philosophicus is trying to describe reality in terms of digital computation. Wittgenstein would have known about this because digital computation hadn't been developed, but the kind of logical propositions he was using was an attempt to do this. Then in his second book, Philosophical Investigations, he developed the notion of a language game. He became dissatisfied with the notion he could pin down reality by mapping it onto something which we would now call digital computation. And he developed the notion of a language game. And a language game is essentially people talking, and it doesn't have to be people, it could be people with a computer, like on Jeopardy. They develop a set of rules for how they're going to converse. And this rules of how they're going to converse make a game where they talk back and forth in a particular way, but the game is what's important, and not necessarily how it corresponds to reality. So, and you know, famously at the end of his book, he said, you know, back to the rough ground. So, meaning he basically threw up his hands and said, I have no idea what reality actually is. So I'm bringing this up as a concern. So, you know, what do we mean by reality? Look, human beings have been trying for thousands of years to figure out what this might mean. We don't even have a clue about that. To say it's analog or digital, I'm concerned about this notion that the very notion that our models, including the very, very powerful digital logical model of discrete mathematics that we have, which are an amazing thing. I see lots of people looking at their computers right now. These models actually necessarily capture reality in a specific fashion. So I'm bringing this up as a concern. You know, even in theoretical physics, which has been extremely successful, you know, because of its success, physicists have a tendency, I wouldn't say to confuse, but sometimes to confuse the notions of their successful models with the actual reality there. So I'm an agnostic on the nature of reality, and so I don't really know what it means to be discrete or continuous. So that's kind of the general stuff that I had to say. I mean, Max, I actually have some rather specific things to say as well for the directed at specific people here. But
go for it.
You want me to do that? Okay.
Yeah.
Okay. All right. So is that actually maybe? But is that? I mean, does anybody want to like harass me for that? I think that
it's fun. We were expecting you to come up and just say, reality is a quantum computer. So now you've given us a much more cautious.
I might say that.
Peppered.
Well, okay, no, I'm not giving you. I was doing this MPhil in philosophy of science at Cambridge, even though I decided not to go in philosophy, was very important for me because I actually realized that when you're talking about things like the nature of reality, that philosophers have been talking about this for thousands of years and actually have many very important things to say. And just the fact that you're like a smart physicist who's like ultra smart and intelligent doesn't mean you can come along and say, well, I'm just going to ignore what everybody's been saying for thousands of years and then like, oh, I'm so smart I can just figure it out on my own. So, which I'm not talking about anybody in this room, because in fact the people in this room are exactly the opposite of this. But many physicists who I talk to about the nature of reality think, I don't have to worry about what reality is, I can just figure it out because I'm so damn smart, right? And I think I realized when I was doing this MPhil that that's a real trap and you shouldn't fall into it. So, when you're talking about things like reality, physics alone isn't going to dig you out of that hole. Okay. So, I don't know, maybe you think it does.
Discussion with us over the problems with it is.
Yeah, that's right. That's the Bill Clinton. Right. That's the Bill Clinton answer. What do you mean by it is?
What do you mean by reality?
Yeah, that's right. Okay.
Couldn't, just to be a little bit provocative, couldn't some people argue that there is some reality out there which doesn't give a damn about whether us humans exist or not? There's an external physical reality there, and physics is by definition a science which has as a goal to try to figure out.
Yeah, I would agree with that statement, but there is an external reality out there that maybe gives or does not give a damn about us, depending on which part of reality it is, right? You know, my daughters like to be fed in the evening, right? So that part of reality doesn't give a damn, at least whether I show up and cook dinner. Right? So, but yeah, most of it probably doesn't give a damn about us. But yeah, but I agree with that statement. But I don't know. It's hard to say what to make that precise in any kind of fashion. I mean, that's like the fundamental philosophical, if not the fundamental philosophical problem, and people struggle with it for thousands of years. Yeah.
So while we're in that train of thought, does that statement assume that we have a final theory, the one of physics, and that we will judge whether it tells us?
Well, you can probably tell from what I said. I
if
actually am
doubtful.
doubtful.
A theory of everything or a final theory, can you actually say something about that?
I'm somewhat doubtful that we may actually come up with a final theory of everything. People have been extremely successful, including people in this room, in coming up with theories of things like theories of elementary particles, which is extremely amazing or remarkable. That's the kind of thing which makes one really believe one's on the right track. We've been less successful about coming up with theories of quantum gravity for a variety of reasons, which I suspect you might talk about. And actually, this is sort of an unfun time for the notion that we're going to come up with this final theory, because you have things like string theory, for instance, which claim that they are the right theory of things, but actually seem to be completely unrelated from anything like experimental verification or stuff that we can actually talk about. So it's not a very fun time to believe that. But if we had a final theory, whatever final theory would be, and it were right, and we got everything right and correct, then that would be fine. And maybe we would then actually go back to saying this is reality. And of course, as scientists, I'm completely guilty of trying to do that kind of stuff. I'm sure that lots of other people here are, and if we can do it, that would be great. But I'm not, it's perfectly possible that we're not going to be able to do it.
But these questions seem dependent on the time in history that we are. So.
Yeah, it's only very recently that we actually have thought, in the last few hundred years, that it seems remotely possible that one could come up with a human theory in the case of physics or science of reality, or really doesn't really mean all of reality, because most of reality doesn't give a damn about what the fundamental laws are, right? But say the fundamental laws of physics, the origin of the universe, and other questions of burning interest. If science were so great, then my students at MIT would be a lot better at getting dates on Saturday night, which is what most people's reality really is. So okay, can I just make a couple of remarks? Because I think that I just want to make a few specific technical remarks, okay, which may be kind of dull for some people. So, is reality analog or digital? So the notion that it's digital or discrete, say that the universe is a gigantic classical computer like a cellular automaton, which is a notion that was proposed by Ed Fredkin and others independently, like Konrad Zuse, back in the 60s. Right. That is a very appealing notion, because we have this beautiful theory of logic and computation, which is actually an amazing theory and really wonderful. And that would be great. And that's perfectly possible, because the Church-Turing thesis says that anything that we can think of as being computable can be computed on a ordinary digital computer, as long as you can keep buying extra memory. Right, that's basically the Church-Turing thesis, and we actually don't have any real counterexample of that. And we can argue philosophically about whether it's vacuous or not. But almost anything that we can do, including quantum mechanics, right, which seems to be the theory that describes the universe, can be computed on a universal computer. The problem is that if you actually look at we have universal computation. It's a very cool model for things. It's a model for digital computation, but it also seems to underlie all kinds of finite mathematics, including all the stuff that we have, like quantum mechanics, where it seems to be continuous, but we can approximate it to an arbitrary degree of accuracy. So this is kind of like stuff for digital side. All right, we only information. We only get finite amount of information about stuff. So one of the other great inventions of the 20th century was the information theory from Shannon, which said that things come in bits. We can divide up information into bits, and we only have a finite amount of bits of information about anything. So that's like this is certainly something which would make you hope that things are discrete. Anybody else want to add something? Other things, evidence that things are discrete right here?
Well, maybe just that even the continuous mathematics is also driven by computable.
Right. I think I tried to say that, but let me just put that there. Right. So most, basically most, if not all reasonable continuous math. Continuous, excuse me. I must say is computable. Where computable on a digital computer, where computable has a technical meaning, which is you can approximate it efficiently on a ordinary digital computer.
And every theorem that was ever proven about continuous math and integral calculus is just a short bit string which was derived in a finite number of steps from a finite set of axioms. So even there, all the stuff that we seem to know about continuous mathematics is totally computable.
Right, so all theorems are computable because theorems by definition are stated in bits or language and then derived by a finite set of steps from that set of bits. So everything like a theorem is also computable. Yeah, so this is all this is good. This is good stuff.
The second point, can you said something about Shannon theory?
Oh, this yeah.
Shannon theory only applies, well, starts from discrete quantities, discrete random variables.
Yeah.
So what do you mean by it? Can you just...
So the amount of information we can get about something is finite. Right? When we make a measurement, right, and you write down the results in some computer memory on a piece of paper, you use a finite number of bits of information to describe it. And even Shannon theory, which deals also with continuous quantities of information, deals with continuous information by effectively discretizing it. So this is actually a point. Let me actually make a more physical version of this. We were talking about this at lunch. So this is an apparent fact. Got to be careful about saying that things are absolute facts in this game. An apparent fact. So quantum mechanics implies that if you're confined to a finite spatial volume, and if you have a cutoff on the maximum or minimum energy, then the number of states, of distinguishable states, which is quantum mechanics corresponds to orthogonal vectors in Hilbert space, is discrete, so countable, plus finite. So that's also pretty good because, in fact, quantum mechanics on its own, the quantum mechanics came about because Planck realized that if you could actually explain features of electromagnetic radiation, which was thought to be made out of waves, by imagining it came in chunks called photons. So there's a kind of innate discreteness in quantum mechanics. And so quantum mechanics, which we believe, which is currently the winner for like most accurate theory of everything to describe all the stuff we know at the fundamental level, weird though it is. And this also makes things, in some sense, finite.
But you must add to that, how big are these numbers when you let the energy go up and let the volume increase? How fast does the number increase?
Right. So specifically, number of bits. It seems, and this is now relies on conjectures about quantum gravity, general relativity. The number of bits in a volume of radius r is basically no bigger than, is less than or equal to, without the factors of 2 pi omitted, r squared divided by Planck length squared. So the Planck length squared is h bar g over c cubed. And where these are fundamental constants of nature that are measured, and they just seem to be there. So it seems, and this comes from the most dense thing out there is a black hole, and as pictures draw, or you have like little zeros and ones that are on the surface of the black hole at the size of a Planck length. So it seems that you can't do any better than this. There's another version of this that tells you about the number of discreteness in time. That is the number of fundamental information processing steps that you can cram into a volume of space-time, so number of ops. is actually, you can show that this is less than or equal to the time times the radius of the volume divided by the Planck length times the Planck time. So it's kind of interesting that there's a discreteness both in space and in time. Or finiteness, maybe finiteness might be better. Finite number of discrete operations in space and in time.
I'd like to make a little comment.
Please.
My philosophy is so different than that, and probably different than everyone here, because I don't see this. I believe that we will find a model of physics, a discrete model of physics is discrete, and I can make a good argument as to why the quanta of length is closer to a Fermi than it is to Planck's length. I know that sounds sort of very strange, but I can give a good argument for it. It takes a long time, unfortunately. So I think that my own conclusion right now is Planck's length. I hate to say this, but in my mind, it's numerology. I don't see any necessity for it except the weakness of gravity, and it's dimensional.
The evidence is just false.
Yes, I still don't see
That's
any
exactly what
evidence
he
for
said.
it.
Well, actually, in some sense, I think this actually fits in with what you're saying, right? Because actually, this picture right here says that the minimum scale for a bit, like for the number of bits you can put in a volume, is not at the Planck scale. The minimum scale depends on the size of a volume and the amount of energy you have in it. So this is actually, for instance, this is not 1 bit per Planck volume. This is 1 bit per Planck length squared on the error, this holographic principle, which Girard was the first person to propose.
Yeah.
So
I'm in another ballgame.
Okay. Well, yeah. So I'm actually, this stuff is stuff that is reasonably well known within the context of quantum mechanics. I'm not actually making any kind of philosophical statement here. Okay. So I'm happy to believe that we might agree or differ philosophically. I'm just trying to
The question is God going to get an A or an F?
God going to get an A or an F. So let me actually
yes, an F if it's
So let me just close by saying, so it's annoying that quantum mechanics is, so why quantum? Because the problem is, let me just conclude what I was going to say, because Max wants me to conclude, so I will conclude. So pro-continuous. The problem is that quantum mechanics has a continuous nature as well. So you could have quantum states 0 or 1, which is kind of the discrete, distinguishable states. But then you can also have this funny feature where you can have quantum states include these continuous superpositions where this alpha is some complex number. So why do we have these complex numbers in quantum mechanics? And there seems to be some intrinsically continuous feature about quantum mechanics, which is very hard to get rid of with any kind of discrete kind of argument. So quantum mechanics is both continuous and discrete. So one of the reasons I like it, I think it might be a reasonable kind of thing. So why quantum? They're actually, this reminds me, this is, Born, Einstein, everybody's thought about this for a long time. However, my feeling about this, again, to try to deflate things a little bit, this is no more or less, I think this is not that different from the famous question from Marx, Groucho Marx, that is, why a duck? Why a duck? This is yeah, who here has seen this movie? Yes, of course. Why a duck? Why a duck? These two questions might be rather similar in terms of their deep ontological status. So I would say, if it walks like a quantum and quacks like a quantum, then it's a quantum. But so there is. I will just say that there is a nice explanation. I'll close by saying there is a nice explanation. Why, who ordered that? Who ordered the stuff? Bits, I understand. Bits are very simple to understand. They're the basis of logic. In discrete mathematics, I understand. Who the hell ordered this? These continuous variables. Why is that on the table? Right. So nobody knows the answer to that.
I do.
Oh, okay, Ed does, okay. Well, let me just say that there's a nice...
What you can have in a discrete system is exact conservation laws. And if you have exact conservation laws, such as exact conservation of angular momentum, or exact conservation of linear momentum, then you get, by a version of Miller's theorem, you get apparent asymptotic continuous symmetries.
I'll take your word for it. This is like super selection rules, like vortex edges and super
No, this
selection
is
rules?
all very simple. In other words, you can have a discrete process that conserves angular momentum exactly, and conserves linear momentum exactly. It's discrete. Okay? And you can show that if you move up above the level of that quantization, you will have, because of Miller's theorem, and that's assuming that there's an approximation to Lagrangian or something, a Hamiltonian or something, then Miller's theorem says that for every conserved quantity you have a continuous.
That doesn't. You mean these are like the symmetries of, for instance, in quantum classical lattice gases, where these conservation laws are preserved at a higher coarse-grained level. Well,
wait, I'm saying you can have microscopic exact conservation of these quantities because, they're like first of all, you understand you can now compute these days with bits where you don't ever, the bits are conserved. You don't have to have an AND bit that makes 0 or 1 disappear. You can use reversible logic.
Okay.
So all these things say that you can have small little discrete quantities around there with exact conservation levels.
Why does that give you complex numbers?
Well,
or you're saying complex numbers are not
there? The model I have now that I'm working with, their complex numbers plays a big role, but it makes it very easy to get a quantum mechanical oscillator. What I believe is that there's a simple, discrete model on a lattice that produces quantum mechanics. In other words, that underlying quantum mechanics is a discrete, deterministic, not so microscopic system. In other words, it's microscopic by our standards, but nothing like Planck's light.
Well, since you seem to have the answers for this, I await eagerly to see them. Since all I want to do was actually raise some questions, make some basic points about what physics actually, current physics as we understand it now, tells us. And I actually had an answer for why a duck. I mean why quantum. But I will forgo giving that and let somebody else talk about what they want to talk about.
Well, I think you've succeeded. Thank you so much, Seth.